Hi everybody, I hope this video finds you well. In today's video, we're going to be taking a look at section 2.8 from your textbook. This is the last section from chapter 2. Remember that for our class, the last set of videos dealt with section 2.6 and we are skipping 2.7 entirely. So 2.8 is the sort of last section that we'll be discussing from chapter 2. After this, we'll be moving into chapter 3. If you do want to see a summary of chapter 2, though, there is a section 2.9, which is sort of a chapter review that might be handy to sort of take a look at. This is going to be a relatively short video because section 2.8 is simply sort of stating a bunch of equivalencies from some of the different sort of theorems that we've done thus far. So this is what's known as the invertible matrix theorem. So the invertible matrix theorem, there isn't going to be much to really do here. We just want to briefly talk about a bunch of equivalencies for some of the things that we've been studying. So once again, we're going to let A be an n by n matrix. Remember, all this stuff about like invertibility and everything like that only applies to square matrices. So for this theorem, you're going to assume that you have a square matrix. Then all of the following statements are equivalent. And what we mean by equivalent is that if one of them is true, then they are all true. And if one of them is false, then they are all false. So either these 5 things apply to matrix A or none of these 5 things apply. So the first statement is that A is invertible. If A is invertible, then the system AX equals B has a unique solution for all n-dimensional B. So for any n-dimensional column vector B, no matter what you put over here, this system will have a solution, and that solution will be unique. Specifically, if you talk about the homogeneous system, AX equals 0, then that'll have the unique solution X equals 0. We know that homogeneous equations always have at least one solution, which is X equals 0. But in the case that A is invertible, then we know that that is a unique solution, X equals 0. If we try to tie this in to rank, then if A is invertible, then this system will always have a unique solution, this guy will always have a unique solution, and the rank of A will be exactly n. Finally, A is row equivalent to the n by n identity matrix. Finally, this actually does wrap around as well. If A is row equivalent to in, then A is invertible and all these things apply. So all of these are if and only ifs. A proof of this is not really necessary. Your book sort of sketches out where all the relevant proofs come from. But if you think about it, all of this is stuff we've already shown. So I'm just going to run through it verbally. To show that 1 goes to 2, remember, if A is invertible, then you could solve this by doing X equals A inverse B. And that will be a solution. How do we know that it's unique? Well, we actually proved that a couple videos ago where we showed that if you assume that you have another solution, well, then it has to be unique because, again, there's a connection between invertibility and rank. So this guy, if you're invertible, then you know you have a unique solution. Obviously, from going from 2 to 3 is very simple. If you let B equal 0, well, then you have the homogeneous system. And of course, we know X equals 0 is always one solution, but since it must be unique, then it has to be that unique solution, X equals 0. All 3 of these can sort of be seen to imply this guy right here, that the rank of A is equal to n. Remember, rank of A equal to n just simply means, well, that you have a full rank, and of course a full rank is necessary here because if your rank was less than full, then there would be a chance that when you augment it with a certain choice of B, the augmented matrix would have a higher rank, which means your system would be inconsistent. But we know from statement 2 that every system has a unique solution, so the rank must be full. Finally, if the rank is full, that means that when you put it in row echelon form, well, that means that every row must have a leading 1, right? So there are no 0 rows. That's if you put it in row echelon form. But, of course, if you put it in reduced row echelon form, then that means you will get to the identity matrix, because the identity matrix is the matrix that has 1s on the diagonal, so in every pivot position, and 0s everywhere else, which would be the reduced row echelon form. So if rank of A equals n, then you know A is row equivalent to in. Finally, to wrap back around, if A is row equivalent to in, then we know that if we take A and augment it with in, we can change A into IN, and what IN changes into, as we do those elementary row operations, will be the inverse, showing that A is invertible. So these 5 statements here are all equivalent. If you look in your textbook in section 2.8, there is a 6th statement that deals with something called elementary matrices. We're not discussing that because that's from 2.7. So these are the 5 statements that for us right now make up the invertible matrix theorem. After this video, we'll be getting into chapter 3, where we're going to be introducing a very important sort of property of a square matrix, which is called the determinant. After we've worked with and defined the determinant, we will be able to come back to the invertible matrix theorem and see that there is a connection to determinants for these things as well. So we'll come back, we'll restate this theorem with 1 or 2 additional equivalencies. So this wraps up chapter 2 for you guys. The next video will be on section 3.1.